Hello everyone, I'm going to present our work about a soft wearable skin brace for assisting forearm pronation and supination with a low-profile design. Neurological disease affects millions of people living with upper limb impairments. They need assistance to enhance their functionality in activity of daily living, such as drinking water, opening doors. Among all upper limb movements, the function of forearm are crucial in performing these ADLs. Previous research focusing on the wrist and forearm rehabilitation can only work in stationary condition due to the non-portable design. And the current research about wearables for forearm and wrist mostly provide assistance for a single DOF and restricting to others. However, impaired upper limb movements in patients usually involve more than a single DOF. So we wanted to develop a compact wearable robot for assisting forearm movements without restricting to other DOFs. There are two challenges for the forearm mechanism design. First is the rotation axis of forearm pronation supination coincides with the forearm itself, which makes the wearable mechanism design challenging. The second, for tendon drive mechanism, when the cable drive robot starts to assist wrist movements, anchoring is needed, while assisting forearm rotation also requires actual support for avoiding unnecessary joint and skin pressure. Basically, the mechanism was inspired by forearm anatomy. We designed the skin brace for assisting the forearm pronation supination based on a real tendon actuating mechanism, which mimics the pronator quadriceps and pronator teres muscle tendon module of the forearm. The skin brace consists of three parts: a wristband that fixes the distal end of the forearm, a cuff connecting the wristband and the proximal end of the forearm, and an actuation module placed outside of the forearm. Two cables fixed on the wristband, guided by the reel and slider, connect to the actuation system through the Teflon tubes and Bowden cables. In this way, the device can assist the forearm pronation supination by driving the wrist to rotate along with the wristband. We quantified the movements of the wrist landmarks during the forearm pronation supination, and we designed the guide rail mechanism as a spiral shape to adapt to the motion of the forearm. The guide rail mechanism enables the slider to complete 150-degree rotation under the constraint of a 100-degree rail without occupying large space. Furthermore, the skin brace can be individually customized by measuring several forearm parameters, which enables us to provide users with a customized brace in a short time. Previous studies usually wrap the forearm spirally with strips and driving the forearm to rotate by the tension of strips length change. However, as the rotation angle changes, the output torque from the device will constantly change, and the tension generated by the strip is along the spiral direction, so it always keeps an angle to the forearm rotation direction, which may cause large pressure on the user's skin and the joints. For the skin brace we proposed, the tension vector of the cable is always highly aligned with the forearm rotation direction to generate pure moment without a singularity of inefficient power. It can provide similar torque at different angles with 70% of transmission efficiency. We conducted user tests to compare the range of motion, output torque, and ADL task performance with and without device assistance based on motion capture system and EMG sensors. The results show that the skin brace can significantly improve the abilities of stroke survivors and provide them with sufficient assistance to complete ADLs such as bottle rotating and door opening. In an unsupervised environment, downing dumping a device is the first obstacle for patients to use independently. We asked all stroke survivors to perform a 10 trials downing dumping test. As we can see, even though it was challenging for the stroke survivors at its beginning, they were able to reduce the time after multiple practice, demonstrating a significant learning effect. We asked all participants to fill a standard system usability scale. The results show that healthy participants generally rated the skin brace lower than stroke survivors, which we attribute to the performance of the device in some tests that didn't match their performance in voluntary condition. In addition, all participants also filled a customized questionnaire to quantify their subjective impression on the device. Both stroke survivors and healthy participants had a more positive impression in terms of the compactness and the wearability of the skin brace. These two video clips demonstrate the skin brace advantage of being able to co-use with a pneumatic device. Meanwhile, the brace is compact enough to be hidden under clothing and make no obvious visual difference when wearing it, which can have very positive effects on patients in terms of social psychology. In conclusion, the proposed skin brace is able to assist forearm pronation supination and providing sufficient assistance to complete ADLs. This wearable device is compact in shape and light in weight. The user-friendly design allows for easy donning and doffing, as well as individual customization, while also have potential for co-use with other reputation devices without other joint movement restrictions. Our future work will be focused on developing wearable robots for assisting all movements of the forearm and wrist based on this skin brace.